Welcome back everyone. In this lecture I will continue with proving Euler's theorem on giving this criterion for Eulerian graphs. So, let us recall the theorem statement. So, we want to actually determine when given connected graph is Eulerian. So, a non-empty connected graph is Eulerian if and only if it has no vertices of odd degree. So, that is what we are interested in proving. So, let us start with forward direction. So, assume that G is Eulerian. So, then we want to conclude it has no vertices of odd degree. So, now since G is Eulerian, so we can actually take C to be the Euler tour of G with origin U. So, now this C being Euler tour, so recall what is Euler tour. It is nothing but a closed Euler trial. So, that means a trial that traverses every edge of G. So, that is called Euler trial and it must be closed. So, the starting origin and terminus vertices must be same. So, this is what we have in the graph G. So, now if we have such graph such Euler tour in G, then what happens? Suppose V is some internal vertex. So, then this V, if we look at it, so each time this some edge actually comes into V. So, like this. So, in the Euler tour, so then it also must exist from V, okay, because this should happen at any given vertex, okay, internal vertex. Since the Euler tour actually traverses each edge of G exactly once. So, whenever it comes into this vertex V, then it has to go out for any internal vertex. So, this and all the edges of G are actually counted in the Euler tour. So, that means, so all the edges that are incident at V, that also will be counted. So, in particularly if we look at the degree of V, that must be even, because whenever you have some edge coming in, then it should also go out. So, if you actually pair it with them in this Euler tour, okay, because this is just a closed trial. If we just write it as like U E1 V1 E2 V2 and so on, then it is clear that we can pair easily the internal edge and an external edge. So, that actually will give even counting for the degree. So, then what happens to the origin? So, origin again, like since some edge actually goes out of origin and then some edge actually comes into the origin. So, because of that this origin vertex U also will have even degree. So, it is just convincing ourselves that so given internal vertex V, so you have some incoming edge and outgoing edge, pairing them gives even degree. Similarly, this origin this origin vertex U also like starts and ends at U. So, then the degree of U also must be even. So, this proves that G has no vertices of odd degree. Okay. So, now what is about the converse? So, let us prove the converse part. So, the converse part is actually proved using this important technique called finding minimal counter example and then getting contradiction. So, what we try to do, we actually look for some kind of minimal counter example and then analyze that counter example and then arrive contradiction to that. So, analyze that counter example and arrive to contradiction. So, that way we can say that by proving by contradiction, so we actually never get such counter example. So, it is a standard method in graph theory that is used in proving many interesting theorems. So, I am going to actually demonstrate such proof in this particular situation. So, we prove the converse using this approach. So, what are we going to do? We want to prove that you have a graph that has no vertices of r degree. We want to claim that that must be Eulerian. But let us assume that we have some graph non-Eulerian connected graph with at least one edge and no vertices of r degree. So, let us say we have actually such a graph. So, then what we can do, we can choose such a graph G with as few edges as possible. Okay. So, that is the minimality that we are putting. So, the minimality is assumed on the number of edges. So, you have G which is non-Eulerian plus connected and let us say number of edges at least one, because we do not want some trivial graph with no edges. So, and then we are assuming that it has no vertices of odd degree. So, this is the assumption. So, like we have an counter example, then we choose this G such that this epsilon G, the number of edges is as minimum as possible. Okay. And such non-Eulerian, if at all there, it should exist because of well ordering property of natural number. So, you can like there are only finitely many graph are there. Okay. So, one on the number of edges, if we just assume okay, minimality, then we can guarantee that we will be able to choose such a graph. So, now once we have this graph, then we need to actually somehow get contradiction by analyzing this. Okay. So, how do we do that? So, let us actually look at this graph. So, this graph actually has this property that each vertex has like all vertices, actually they have even degree at that vertices. So, that means so given vertex V, so there are even number of edges. So, that means whenever I choose to go in using one edge, then I can choose another edge to go out. Okay. So, there is a choice at each vertex. So, that actually kind of gives us that we can always have a closed trial in this graph. So, maybe this is somewhat trivial observation. So, I will leave it as exercise. So, prove that G has a closed trial. So, since each vertex of G is even, okay, that means has even degree, we can have a closed trial in G. Okay. So, you can actually induct maybe on the number of vertices or number of edges. Okay. It's not very difficult to prove this. Okay, so since each vertex has even degree, we have actually a closed trial in G. So, then what we do, we just choose a closed trial of maximum possible length in G. So, let us say C. So, this is a closed trial in G. Okay, choose this closed trial in G such that this has maximum possible length in G, such that C has maximum length in G. Okay. So, there are only finitely many closed trials possible. So, we can choose the maximum length. So, if C is already Euler Tour, then we are done, but we are working with the counter example. So, C cannot be Euler Tour. So, C is not an Euler Tour of G. So, that means it has to miss some edges from G. Okay. So, if we actually take the edge set of C and then remove it from G, then this should have some edges. So, should have some edges. Okay. So, now what we can do, we can actually write this as union of connected components. So, then we can choose a connected component, let us call it G dash with the number of edges being positive. So, choose G dash a connected component in G minus E of C such that the epsilon G dash is positive, okay, because that is possible. So, this has definitely some edges. So, then it will be written as some connected union of connected components, then we are choosing G 1 that has some edge in it. Okay. So, that is what we are doing. So, now let us actually go back and understand some property of C. So, C is being a closed trial. So, in particularly this is Eulerian. So, why this is Eulerian? Just to look at the subgraph C. So, by definition of Euler Tour, it has Euler Tour. So, that means because C itself is a Euler Tour for the subgraph C. So, it must be Eulerian. So, the argument that we saw in the beginning. So, each vertex if there is an incoming edge, there should be outgoing edge. So, by looking at the counting of degree for each vertex, then we realize the degree of each vertex in C. Okay. So, treat C as a graph itself. Okay. So, then if I take any vertex in this vertices of C, then the degree of that vertex must be even. Okay. That is because C itself is Eulerian. So, now if we look at the original graph. So, the original graph for any vertex. So, what we have in the original graph G, the degree of any given vertex is even, and now the degree of this vertex, if it appears in capital C, so that is also even. So, that means when we look at this degree of this vertex, let us say this vertex happens to be in the intersection of vertex of G dash and C. Okay. So, let us say yeah, we do not need to worry about G dash. Anyway, so if it is an intersection, it is okay, otherwise this degree is going to be 0. So, I want to understand what happens to the G dash, which is the connected component of G minus edge set of C. So, now what is the observation that we making? Suppose you have a vertex which is in C and as if you think that vertex as element of the original graph, then the degree of that is actually even in the original graph and it is even in the subgraph C. So, that tells us that once we remove all the edges that appears in C from G, so then whatever that degree that going to be remaining in this complement graph, which is G minus E of C, so that is also going to be even. So, the degree of, okay, let us write it like this, degree of G minus E of C of V. Okay. So, since these two are even, so then this is also must be even. Okay. So, why that is the case? So, you have a vertex and you have couple of edges in G. Okay. So, then what you are doing, let us say these edges are actually part of C. So, the blue edges are from C. So, then we just removed it. So, then whatever the red edges that are going to remain in G minus E of C, that is going to be even. So, we have even number of edges and we are removing even number of edges. So, the remaining edges must be even. So, that tells you that all the vertices in G minus E of C, they must have actually even degree. So, that means it has no vertices of odd degree. In particularly, any connected component must satisfy the same property that it has no vertices of odd degree. So, in particular we have that G dash has no vertices of odd degree. Now, note that G minus E of C obtained from G by deleting some edges. So, that means the number of edges in G dash must be strictly less than the number of edges in G. So, now we have already assumed that G is our counter example. So, that means with we have chosen G such that that epsilon G being as minimum as possible. Since epsilon G dash is strictly less than epsilon G, that would imply that G dash must be Eulerian. This must be Eulerian. So, then that must contain some Euler tour in it. So, we can call that Euler tour as C dash. So, we have this G dash. So, then inside that we have this C dash, which is Euler tour of G dash. So, now note that our original graph G is actually we have, and then we have obtained this G dash as a connected component of G minus E of C. That means, in our original graph we just deleted some edges and then obtained this G minus E of C. So, in particularly G dash is just one connected component in G minus E of C. So, since the vertices are not changed, indeed the vertex set of G minus E of C is same as the vertex set of G. So, and original G is connected. So, that implies that we must have actually one vertex common between G dash and our C. Okay. So, there should be a vertex V in V of C intersection V of G dash. Now, note that so we have actually taken this Euler tour C dash inside G dash. So, again like C dash actually traverses through all possible edges of our original graph this G dash. So, that actually tells us that we can assume this V is in this intersection of this C and C dash. So, we can assume V is in intersection of VC and VC of this. So, this just follows from the connectedness of G, nothing more. So, now if we draw the diagram, let us actually draw the diagram like this. So, you have this vertex V and then you have this C dash that is inside your G dash. So, then you have this already another closed trial which is C dash. So, let us use some other color. So, that is actually kind of starts with starts with V and then goes around something like this. So, this is my C and this is my C dash. So, both C and C dash share only this vertex V. So, if you think about it, the subgraph C and C dash, it can only share some vertices. So, because C dash is completely contained inside G minus E of C. So, C and C dash they do not share any, share no edges common. So, that actually allows us to actually look at this concatenation C dash and C, because what we can do, we can first go around C dash and then come to V and then again we can go around C and then come back to V. So, now this concatenation actually gives us bigger closed trial, and again it has the origin V and terminus V. So, this is a closed trial inside our G, such that if you look at the number of edges inside this closed trial. So, then this is going to be strictly greater than the number of edges in C, because you have actually concatenated two closed trial and then created new closed trial, and C and C dash they share no edges. So, that means you are adding some new edges in this process. So, that tells us that the number of edges inside this new closed trial must be bigger than actually strictly bigger than the number of edges in the old closed trial C. But that produces contradiction, because we have assumed from the beginning that C is a closed trial of maximum possible length in G, but we have produced a new closed trial which has much more length. So, that actually gives us contradiction. So, if we go back to the choice of C, we can see that we have actually chosen C such that this is of maximal length possible. So, this contradiction that we got by assuming a counter example exists. So, that actually tells us that we cannot have any counter example. So, that proves actually the converse of the theorem. It is a very nice method that is used in various places in mathematics, especially in graph theory. You assume that a minimal example exists and then you analyze that minimal example and then get some contradiction. So, that is a very nice method. Let us see some corollary of this result. So, one of the important corollary that we get immediately is that when one connected graph has an Euler trial or not. So, we can immediately prove. So, maybe I will leave it as exercise, because it is not a very hard thing to prove. So, a connected graph has an Euler trial if and only if it has at most two vertices of odd degree. So, we are not talking about Euler tour, we are only talking about Euler trial. So, if you can allow two vertices of odd degree. Note that we have observed already the number of vertices that have odd degree must be even. So, that means either you have no odd degree vertices, in that case it is Eulerian, or if there is one odd degree vertex, that would imply immediately there should be two odd degree vertices. So, now how do you prove this? If you have G, for example, the converse part is what somewhat involved. For the converse part, if G satisfies this condition, so then you have two vertices of odd degree. So, then what do? You introduce a new edge between them. Okay, you introduce an edge E between that two vertices. That means you are adding an edge with G plus E. So, now adding an edge actually makes those two vertices also having even degree even degrees. So, that would imply that G plus E becomes Eulerian. So, then you will get Eulerian tour. From the Eulerian tour you delete that edge. So, then you will have your Euler trial. Okay. It is a rough idea, one can make it very precise and then write details. I will leave it to you to do that. Okay. So, this even though like sounds like some theoretical result, one can actually kind of play some games using such results actually. So, for example, one can actually draw some graph on the paper and ask the opponent challenge that whether given figure can be drawn without lifting one's pen from the paper. Okay. So, you can actually come up with any type of graph and then challenge them. It is a nice game that one can prove, one can play. By our theorems we already know, for example, Euler tour exists if and only if all the degrees are even and so on. So, so you can also challenge whether you will be able to come back to the starting point, or for example, you can also use it for actually getting only the Euler trail, which tells whether you can actually draw without lifting the pen. Okay. So, one can actually challenge the opponent and then play such games. So, most of the graph theory problems they have all these motivations coming from designing some games or challenges. Okay. So, I would actually recommend you to go back and then read some of these motivations that will help you to understand the theoretical part. Okay. So, I will actually discuss briefly about one more concept called Hamilton cycles and Hamilton paths. Okay. Then I will actually I will stop with that. So, what is Hamilton path? It is a path that contains every vertex of G. Okay. So, before Eulerian tells us it is a trial that contains all edges. So, now Hamilton path is nothing but it is a path that contains every vertex of G. Okay. So, a path that contains every vertex of G is called Hamilton path of G. And what is Hamilton cycle? So, we just remove this path by cycle. Okay. Again, a cycle that contains every vertex of G is called Hamilton cycle. Okay. A graph is called Hamilton if it contains a Hamilton cycle. So, a graph is called Hamiltonian. Okay. Not Hamilton, Hamiltonian. So, let me just write it. G is called Hamiltonian if G has Hamilton cycle. So, it is actually good to have some nice non-trivial necessary and sufficient condition for a graph to be Hamiltonian, but unfortunately we do not know any such criterion. in fact, the problem of finding such condition is one of the main unsolved problems of graph theory. Okay, one can actually come up with some necessary condition, but yeah, we do not know any if and only if conditions that actually characterize Hamiltonian graphs. So, again this is also like the Hamilton path or cycle finding. So, this is related to some game called Icosian game, okay, that is played played generally. Maybe I will leave it to you to actually Google it and then like read about it more. Okay, so I will stop here with this discussion about Eulerian and Hamiltonian. So, in the next class we will actually discuss briefly about matchings, perfect matchings and so on, and then later quickly get into vertex colorings, and then I briefly explain what is chromatic polynomial and some other interesting polynomials related to colorings and graphs. Okay, then with that we will end. I will stop here, right, for time being. Yeah.